let's say I've calculated the mass moment of inertia of something about the center of mass for rolling purposes or spinning purposes, and then I realize I actually want to do my analysis of the motion about another point. So maybe I want to do it about where it touches the ground because I'm thinking about it as a rotation around the ground. Or maybe I want to do it at some other weird place because I'm considering making something that has some off-kilter rotation. I had a really fun little wind-up toy as a kid that used off-kilter rotation to make it jump around. Sometime I'm going to get that and show it to you. But how do we do that? I don't want to have to redo all those integrals at these funny points. That would be pretty difficult, actually. So instead, mathematicians have saved us, and they have proved the parallel axis theorem. And the parallel axis theorem says that the mass moment of inertia about any other parallel axis, I'll just use the letter G, is equal to the mass moment of inertia about the center of mass. So this will be the axis that goes through the center of mass plus the total mass of the object times the distance between the axis O and the axis G squared. So for example, if I had that ring and I've calculated the mass moment of inertia about the center, but I now want to do it about this axis G, both of these are axes that are going into the board, so they're parallel, then I would just have this distance here as my distance. So I should say that the I sub G is the mass moment of inertia about an axis parallel to one through the center of mass. And that has to be the O. So the IO is a mass moment of inertia through the center of mass. And that's really important. About an axis through the center of mass. Here M is the total mass of the object. Of the object. And D is the distance between O and A. Or G, I mean, excuse me. So be careful here, even though this is D, in my little example that I drew up, it's actually the radius, not the diameter. So don't let that D notation confuse you. And then just making sure it's through the center of mass, again, is super important. And the reason is because you can imagine, what if I switched these? What if I said, oh, the mass moment of inertia of O is this one over here, and then we're moving to G, which is the center. This will always increase the mass moment of inertia. But in fact, this object is easiest to spin about its center of mass. That's where all of the mass is closest to the center of rotation. And the closer mass is to the center of rotation, the easier it is to move things. And as we move that to farther away from the center of mass, the harder it is to move something. We might not notice it as much in this little thing, but if we have our center of mass here, let's say I just am about the center of mass here, that's pretty easy. And if I move somewhere really far here, and now I try to move it, this is much harder to swing this here because I'm farther away from the center of mass, where all the mass is located. So this will always, the parallel axis theorem will always make the mass moment of inertia bigger, which is why we always have to go from the center of mass to some other parallel axis. We'll do an example of this shortly, but this is a really useful tool in calculating mass moments of inertia.